So there you are. All right, so the first talk in the session will be given by Max, talking about program logics a la carte.
Thanks for the introduction. My name is Max Vistrup, and this is joint work with Michael Sammler and Ralf Jung. So here's a story, and perhaps it's a familiar one. We have a young researcher who sets out to define a programming language, language 1. Perhaps this programming language supports certain effects. Perhaps there is an output effect, programs can write to the console. Perhaps there's also a crash effect. Certain programs are malformed, and therefore they crash. And perhaps there's also a heap effect, which is to say that certain programs may want to read or write memory. Now, the researcher is interested in proving certain programs to be correct. That is to say, proving the absence of bugs. There is one good way of doing so, which is to devise a program logic. So that's what the researcher does. They devise a program logic, logic 1, that is tailored for this programming language, language 1. So a program logic typically consists of two things. So for one, it consists of a number of proof rules that you can make use of in order to build up proofs for correctness of programs. Furthermore, it also has a soundness proof, which guarantees that these proof rules are indeed correct. Now, sometime later, this programmer or this researcher might be interested in a new programming language. Perhaps they devise a new programming language called language 2. This programming language might have another set of effects. Maybe it has crash effect, maybe it has heap effect again, but maybe it also has concurrency. Again, the researcher is interested in proving the correctness of certain programs. So they, again, do the same rigmarole of defining and establishing a program logic now tailored for this new language, language 2. Notice here that the two languages, language 1 and language 2, share a significant overlap. We can quantify this overlap by looking at what are the effects that are shared. So in this case here, we have that the crash effect and the heap effect appears in both languages. So one concrete consequence of this significant overlap is that there are certain proof rules that appear in both of the program logics. So for instance, you might have a load rule, which looks something like this, that appears in essentially the same form, whether in logic 1 or logic 2. There is one unfortunate fact or consequence of this, which is that when you come down to logic 2 and you want to establish its soundness, you are incurring duplicated proof effort, right? You've already proven this proof rule to be sound when you established logic 1, and now you're establishing logic 2 and you're doing the same thing again. So this is a frustrating situation because it means that researchers are again and again defining new program logics, proving them sound, and is doing much of the same work over and over again. So this seems to evince the need for some kind of lacking abstraction that can streamline the process of defining new program logics. And it is the purpose of this work to establish that abstraction. So let me just sort of adumbrate like a very high-level overview of our solution. So in our view, we take a language like language 1, and we view it as composed of certain effects. In this case, there are 3 effects that we've identified. For each of those effects, we take a corresponding program logic fragment. So you can think of a program logic fragment as kind of a program logic that pertains to a particular effect. These are defined in our theory or in our library. Then we put together these program logic fragments in order to obtain a program logic tailored for our particular language. So essentially, we obtain these program logics by composition. Now, to be slightly more concrete, what we are doing in order to implement this solution is the following. So we are interested in defining a language-specific program logic. Now, this language-specific program logic comes in the form of a Hort triple, like this. So the first thing we do is we take this expression in our programming language, and we denote it into some kind of language-agnostic domain that captures the semantics of this expression. Once we have done so, we take the Hort triple of that denotation with respect to a language-agnostic program logic. To distinguish between the language-specific program logic and a language-agnostic program logic, what we do is we use these double curly braces. So that is the idea. We define a language-specific program logic as a thin wrapper around a language-agnostic program logic. Now, let's take a look at this language-agnostic domain. So we are in search of a denotational domain that can capture the semantics of expressions, whether they're in language 1 or language 2 or any number of other languages. So for this purpose, we choose I-trees, which is a denotational domain that is established in prior research and they've proven to be very convenient and successful at modeling the behavior of programs. Now, you don't need to know much about I-trees in order to follow this presentation, but there is one thing you do need to know, which is that it's a data type like this, I-tree ER. And there are two parameters. So first, there's the E, which is the set of effects that the program can exhibit. Secondly, there's the R, which is the return type. That is to say that I-trees have the capacity to return a value, and this value will be of type R. So let me just give a brief overview of the structure of the rest of the talk. So the first thing I want to discuss is this language-agnostic program logic. And this comes in the form of a program logic for arbitrary I-trees. With that, we are going to give an easy and compositional recipe for defining your own custom program logics for your own custom programming languages, or existing programming languages for that matter. Then, to exemplify how this would look in practice, we are going to give a small demo example and see how this recipe is implemented. So let's take a look at this Hoare logic for general I-trees. So this comes in the form of a Hoare triple, where the T here is an arbitrary I-tree. So that is to say that this E is an arbitrary effect set. We are not tied to a particular choice of effects. It's arbitrary. What this Hoare triple is supposed to codify is something like what appears on the right-hand side, namely that if the precondition is satisfied, every execution of the I-tree goes well, and the output will satisfy the postcondition. Now, there's one caveat here, which is that the effects in E do not carry any logical meaning just yet. So it's necessary to endow them with a logical meaning. And this is where this subscript H comes into the picture. So H is what we call a logical effect handler, and it specifies an axiomatic semantics to the effects in this effect set E. That is kind of the datum that is the input to our definition. Once you have that, you get, from our theory, this definition of a Hoare triple for I-trees with effect set E. Furthermore, there's a theorem in our paper that I will not discuss so much today, but that ensures that this Hoare logic for I-trees is in fact sound. Now, there are certain rules that come for free with this definition. And I emphasize for free, right? You don't need to reproof these rules for every effect set E. So the first one is a familiar rule. It's a consequence rule, right? It's well known from Hoare logic. Furthermore, we're actually working in a separation logic, and we get a frame rule for free. Then there are certain rules that pertain to the monadic structure of I-trees. So I-trees are a monad. What that means sort of concretely is that you can sequence computations. So if you sequence two computations together in the I-trees, then you, in order to prove the Hoare triple for such a sequence computation, all you have to do is to prove the Hoare triple for the first computation and then the second computation. And this idea is exactly captured by the spine rule. Furthermore, there's a rule that says exactly what you have to do in order to prove the Hoare triple for an I-tree that just immediately returns a value. Now we have all the ingredients to set out a recipe for how to easily define a program logic. The very first step of this recipe is that you have your language, and you want to identify what are the effects that programs in this language can exhibit. So you build up an effect set. The way you do this concretely is by pulling common effects from our library, from our theory, putting them together. Now, it might also be that your language has some more esoteric features which necessitate custom effects. And in that case, you'll have to define your own custom effects, but you can put them together with these common effects. Once you've done so, you need to specify the semantics of the language. And the way we do that is by means of denotation. So you define a denotation that for each expression in the language associates an I-tree that captures the behavior or the semantics of that expression. Then you need to choose a handler. And the way this might seem like a complicated thing to do, but it's actually fairly simple. For each of those effects, E1, E2, and so on, that you pulled from the library also provides corresponding logical effect handlers that deal with those effects. And so you just put those handlers together, and in this way, you obtain a handler H. Now, this is exactly what I mean when I say combining program logic fragments. Each handler, say H1, H2, engenders a program logic, and we're putting those together in the step. Namely, to define the Hoare triple, we use the denotation, and we use the I-tree Hoare logic according to this formula I already showed. Then, finally, you have your proof rules that you're interested in proving sound. And to do so, what you do is you use the Hoare logic for I-trees in order to do these soundness proofs. That is to say, we have these rules that I already wrote up before, and you can use those in addition to other rules that I've not displayed yet. So in order to illustrate how this would work in action, I'm going to show it by means of an example. So this example is, I call this lambda h. It's a small language. It's a lambda calculus that supports heap manipulation. So I have excised most of the definition that has to do with sort of the lambda calculus aspect of this language, just to focus on the memory aspects of this language. So for the value case, there is one new kind of value, which is values that are denoted by L. These are the locations of the language. These are locations of the heap. Then there are three new kinds of expression. One is the allocation expression, which allocates a new heap cell. Then there's a load expression, which loads from a location. And then there is a store expression, which stores at a location. So in order to implement the recipe, what we have to do is we have to give a denotation. So that is to say, for each expression in this language, we're going to associate an I tree. In this case here, the effect set is going to be composed of the crash effect and of the heap effect. We'll see in a moment why these are the two relevant effects. Now let's focus on just the denotation for the load expression. So the denotation will look something like this. First, we take the argument of the load, and we evaluate that down to a value. Once we have done so, we assert that that value is in fact a location. If it is not a location, we do a crash. So this here is marked in, the crash is marked in red, which is to say that it is what exhibits the crash effect. Once we have done so, we exhibit a load event to load from the memory. This is marked in blue because it marks the heap effect. And finally, we return the value that we loaded from memory. That is the denotation of load. With this at our disposal, we can define the Hoare triple for our particular language, lambda h, according to this formula. To do so, we need to choose a handler h. Now, we know the effect set E was composed of the crash effect and the heap effect, so we simply compose the corresponding handlers to build up the handler h. Then we need to derive our proof rules for this program logic lambda h. And let's just focus on one proof rule. So I want to focus on the load rule. Maybe this is a familiar load rule if you know about separation logic. It says that in order to do a load, you need permission to do so, and the permission comes in form of this points to resource. Now, remember that we defined our Hoare triples as just a thin wrapper around a I-tree Hoare triple or a language-agnostic Hoare triple, and therefore, it actually turns out that this load rule is an easy consequence of a more general load rule. I call this the load rule to rule them all. This rule is a part of the program logic fragment for the heap effect. Now, what is the significance of this? Well, it means specifically that if you have any number of program logics in which this load rule appears, in order to prove the load rule sound in any of those program logics, all you have to do is to leverage this general load rule. That is to say that we do not incur this duplicated proof effort when we define new program logics like this. And I think this is the key point. If you want to take anything away from this presentation, it's this. The theory here allows us to make use of language-agnostic program logic in order to build language-specific program logic. Basically, it adds this layer of abstraction, which comes in the form of the I-tree Hoare logic, that you can use when you're building up these complicated soundness proofs or your complicated custom program logics. So that in particular means that you get to leverage all the good qualities that you know and love from program logics, like reuse and separation and compositionality and local reasoning. You get to leverage those when you build your program logics. And I think that is quite neat. So as a kind of conclusion here, I want to summarize some aspects of program logic fragments. So we had this example language, lambda h. We viewed that as built up of these two effects, a crash effect and a heap effect. Then we took the corresponding program logic fragments, we put them together in order to form a program logic that is tailored for lambda h. A program logic fragment consists of the following pieces. So for one, it consists of a logical effect handler. That is what defines the program logic fragment. Furthermore, it comes with certain proof rules. So for instance, in the case of the heap program logic fragment, it comes with a load rule. And furthermore, it also comes with a soundness proof that it guarantees that those proof rules are indeed correct. So here's some things that are not covered in this talk, but are covered in the paper. So if any of these things pique your interest, you can check out the paper. For one, we have a formalization of the entire theory in ROC using iris, the iris separation logic. Furthermore, we have a very nice logical treatment of cooperative concurrency, which we use to model preemptive concurrency. Then we have a good account of compositional soundness proofs. So we have soundness results for each of these program logic fragments, and we demonstrate how you can put those soundness results together in order to obtain soundness for the entire I-tree Hall logic. Then we have support for angelic choice, and moreover, we have support for mixed angelic and demonic choice. This is something I'm quite proud of because this often presents a difficulty when you're working with program logics. And we have a unified account of termination-sensitive and termination-insensitive reasoning within one framework. And then finally, we have some case studies. So we have an ML-like language known as heaplang. This was established in the IRIS line of research. And we also have a realistic model for assembly known as ILARIS, which is established in the Sammler et al. Work. And in each of those cases, we demonstrate that there is, in fact, less proof effort needed. So I hope some of these points can convince you that this theory is not just meant for toy examples. It is actually possible to invoke this theory at scale for realistic programming languages. And that is all I got. Thank you for your attention. I'm happy to attempt to answer any questions.
Microphone. Yeah.
Thank you. First of all, here. That was a great talk.
Thanks.
I have like 3 questions I need to select. First of all, in realistic languages, the load rule is very different for each language. Like loading a value in C is very, very different from loading a value in JavaScript or in Java. So how much for real languages do you think you can reuse stuff?
I would say so. You have your denotation for load, whether it's in C or JavaScript, and that might do all sorts of complicated things, right? It might say, oh, if you do this, this would be UB, and we exhibit a crash. But when you're approving the load rule, you're making use of, in particular, this bind rule that I showed to kind of step over the individual components of your denotation for load. And then at some point in that denotation, there will probably be exhibited a load effect that interacts directly with memory. That is where we invoke the load rule. But that doesn't mean that there isn't all this like complicated reasoning on the I-tree Hall logic level of abstraction that describes what happens in these cases where there's UB or something. So it's just that the load event maybe appears inside somewhere in this denotation.
Okay.
Yeah.
I will go offline for the next one.
Right.
Oh, we'll get to you.
We'll get to you, don't worry.
We'll get to you. Don't worry. There's time.
Over here now.
Yes.
Yeah.
I wanted to ask how you handle higher order programs, given that with I-trees you have predicativity restrictions of inductive definitions, so it's hard to have intermediate computation results using the same type.
This is a very good question. And in fact, one of the case studies, heaplang specifically, has higher order. You can store lambda terms on the heap, and we support that. There's no issue. So the trick is a bit like we have 1 foot in the semantic world and 1 foot in the syntactic world. So specifically, when we store stuff on the heap, we store the syntactic representation of the lambda term. Then when we pull it from the heap, because there's a fixed point combinator for I-trees, there's no issue. We can actually evaluate that. However, this is maybe not an entirely satisfactory account if you're interested in equational reasoning, because the bisimulations on I-trees are too strong when you have like syntactic representation. And this is what gives rise to maybe the interest in something like guarded interaction trees, which are entirely denotational, right? You can do equational reasoning, but also limited in some ways, at least at the present moment, to my knowledge. Like there's lack of support for non-determinism and for concurrency. But nonetheless, we sort of use the syntactic representation in order to deal with this issue. Yeah.
Yeah.
Your approach is based on the fact that if you extend the language, you just add more effect, but you don't change the previous one.
Yes.
And this is not general, because, for example, take our logic for sequential program. Suddenly you go to concurrency, but with weak memory model. And then the evaluation of an expression becomes completely different.
Right.
And the previous logic is no longer valid.
So I don't know much about weak memory, but I can tell you what happens in the...
It's very difficult.
Yeah, that I believe. I've heard rumors, right? But I can tell you what happens when you go from sequential to concurrent. In fact, you do just add another effect. It doesn't break the previous effects. However, the way we treat concurrency, we model is using what is called using cooperative concurrency. So That is to say that if you just add the concurrency effect, and then the same programs will still verify because you don't have these yield expressions anywhere in the program. So the difference, the breakage really comes in when you're inserting the yield expressions.
But this does not answer my question.
No, maybe it doesn't. No.
Case where,
Yeah.
you can apply the previous thing.
Yeah, I mean, there's also an entire line of research that sort of does this weak memory modeling in Iris, but I'm not so familiar with it.
I think it's a good discussion to take offline.
Yes.
Let's thank Max again for a great talk.